Why PLCs? Well, to control something, they had coils and they had contacts. You might have heard the term relays and relay logic. So where did it really start? You had a contact coil and a contact, and that's how you made a connection. So they had basic relay logic. So when they talk about relay logic, this is a simple circuit. You had a push button, some limit switches, a timer, a motor, and that's basically what you had for relay logic. You had L1, that was one side of the rail, the other side was L2, and the ladders in between were called rungs. That's why it became ladder logic, because it looks like the rungs on a ladder. This is what happens when relay logic goes amiss. You have lots of wires, you have lots of relays, lots of points of failure. And if you have to make a change, good luck, because the prints are very hard to read and a lot of red lines for all the changes. So they came up with what they said, programmable logic controllers. It was initially designed to replace all that relay logic. So you wanted to be able to sequence device activations, coordinate activities, and accepts inputs from a series of switches and sends outputs to devices or relays. But one thing to make sure of is how much is a byte. You've heard of megabits and gigabits, but now we really want to talk about bytes and bits. Each bit represents either an input or an output. So when someone says they just want to turn on an output, they're turning on a single bit, that's what they're talking about. But a PLC has certain components in it. You can see that it has an input module, an output module, a power supply, the central processor unit, some memory. So you have the input module, which is going to take care of all your inputs, your switches, your contacts, and the outputs that would drive relays or motors or actuators. But where is this data stored? And it's what they call in a PLC map. The PLC map has three major components. It has a configuration data table, which means all the configuration of my I/O and how things are put together is in this configuration data. It has an input data storage area where all the inputs from the switches are going to be stored, and it also has an output data storage where all the outputs are going to be stored. The programmable logic controllers replaced relay logic in the 1980s, and it's made by many manufacturers, each with their very own programming style. So you have Siemens and Allen Bradley, Omron, Mitsubishi, Schneider, Rexroth, and PLC Direct, just to name a few. Now they have PLCs, and they put them in these cabinets, and they're called IP20 style PLC control cabinets. IP, that's another nomenclature you'll hear about. IP20 means it's dust protected. It can handle dust, but it can't handle water. If it's an IP65, it can handle splash of water, but not be submerged. An IP67 would be I can submerge it up to 3 feet. So them are the kind of IP ratings that you might hear someone talk about, an IP65 device or an IP20 device. If they say IP20, it's going inside of a cabinet, such as this. So cabinet space, it takes up a lot of floor space. If I have a lot of floor space, that means I can't put production equipment in that place because the cabinet's taking it up. So there's now a shift towards IP65 or IP67 PLCs, such as we have here. There's also robots. The robots have controllers inside them too. And end-of-arm tooling has its own network, and the network would be controlled by the robot controller itself. Each robot controller has a network that's either an Ethernet IP. That means end-of-arm tooling is usually going to be the same as an Ethernet IP. It'll follow whatever the major network is in the front. But each robot manufacturer has a robot controller, and it works just like a PLC. So when we talk about conventional wiring, as you see here on the screen, everything used to be hardwired. And a lot of plants still have hardwired to the inputs and to the outputs. Each valve would require one wire for each bit. Remember, each bit fires one valve and a ground wire, so you got a common ground, but you have an output to fire each valve. Inputs are the same way. You might have a common plus and a common minus, but each input is one bit. So as you see, a lot of wires, a lot of points of failure, because each connection is a point of failure. In the world of electronics, mechanical or electrical, connections are the number one failure. Think about it when you're at home. The first thing when something doesn't work, what do? You go wiggle the connection. Same in the industry. Looking at a 25-pin valve connector on a manifold, again, lots of connections, lots of wires. Each one is a point of failure. So when you look at a traditional wiring system that's still out used in the plants today, you have here in the PLC, you have all the inter-terminal connectors that are out in the plant floor, and each one has a point of failure. For each point that they have a sensor or a wired to it, goes back into a major cable that goes back into the PLC, onto a terminal strip, from the terminal strip up to the I/O card. Again, lots of points.